register anyone? Yeah. Everyone got it? Yeah. I reiterate the point that, although we're focusing on equilibria, remind you that this topic is tied in very tightly with rates of reaction. There's a lot of questions which ask you to consider. There's one nice example of a 6-marker in there, which we'll look at in a bit, which will consider the effect of position of equilibrium as caused by one factor, but also the effect of those factors on rate of reaction as well. So try to keep in mind when you're doing your paper 2 revision, when you're doing your paper 2, that these two themes, equilibrium and rates, are kind of tied together. Right. So I'm going to do literally a little 5-minute, if that, mini review, very short review is the plan, and then move on entirely to exam questions today. Okay, so it's a bit different to what you might do, what I might do at least in a revision lesson. So very briefly, an equilibrium reaction is a reaction which is reversible. Okay. So I know this is kind of basic stuff to start with. It might be a reaction like this one, A and B reacting together to give product C, and they might all be gases. Right, so we've got to be able to define a couple of things. So we've got to put a couple of things on flashcards, probably. So the definition of dynamic equilibrium should be on a flashcard, and it will be when the rate of the forward and reverse reactions are the same. And in that definition there, you're making it clear you understand it's a reversible reaction. If you want to add that to your definition, say it's a reversible reaction when the rate of forward and reverse reactions are the same. You're kind of implying it by saying there's a reversible reaction there. And you should know also that this can only happen in a closed system. And a closed system is one where things can't escape. Things are not going to be lost. Things are not going to be added to the pot as it's going along. Right. So that's a definition you put on your flashcards before we get into the kind of what's going on in equilibrium reaction, and before we get into having a look at the exam questions. So when we're looking at the equilibrium, we've got to consider what. Thank you so much,
I'm really
Miss.
sorry, I actually didn't notice you down there. I had a very loud conversation with some of your attendants.
No worries at all.
I'm really sorry.
That's fine. We'll
Happy
tuck into
Friday,
those in a bit. Cheers. See you. Right. So can we think about the factors? Thanks, folks. So when we're looking at these equilibrium reactions, we've got to think about what factors can affect the position of equilibrium and why, and be able to explain that in exactly the way the exam board want us to. The explanations in reality are deep and complicated, but we've got to give GCSE answers, right? So the answers got to be set for your level. Let's make sure we're answering like the exam board wants us to. And also we've got to think what effect would those factors have on rate as well. So the kind of things we might think about are pressure, temperature in particular, but also maybe adding or taking things away from the reaction. Right. So I'm going to use these as a couple of examples. So we're going to start off by thinking about pressure here, to emphasize the point of what equilibrium reactions do when you change the conditions, or when an external person does something to the reaction. So the idea we've got to get into our heads when looking at equilibrium reactions is that whatever we do to the reaction, or whatever is done to the reaction, the equilibrium will shift to oppose that change. That's the big message, really. So when conditions are changed, when conditions are changed, equilibrium position changes to oppose the change. In fact, it really minimizes the change. So if I heat a reaction up, it will do something to try to cool down. It will shift position of equilibrium to try to cool down a bit. If I take the temperature from, say, 300 Kelvin up to 400 Kelvin, or 100 degrees up to 200 degrees or whatever, equilibrium will shift to try to minimize the change. Or if I increase the pressure it will try to decrease it a bit. Right, so let's look at that example with this equation. So we've got to consider here the fact there are 2 moles or 2 molecules of gas on the left-hand side and only 1 on the right-hand side. That's the kind of language we'd use in our paper. And so if I increase the pressure, it's going to want, or the reaction will shift to move to the side with the fewest moles of gas, which is the lowest pressure side. So if we can agree that 1 mole of gas would exert less pressure than 2 moles of gas, if I increase the pressure, it will go to the side which would exert less pressure, the right-hand side. Okay. If I increase the temperature, as I said before, and this reaction is exothermic, and you would see that by saying delta H is negative, it will try to increase in temperature. It will move in the endothermic direction. It will shift, the equilibrium will shift to the left. But before we get on to looking at exam questions and practicing this, I just want to highlight something, a term called equilibrium yield, which often confuses people. So equilibrium yield is just a way of saying how much of the products are formed. So if the equilibrium is lying way to the right, we've got a high equilibrium yield. So high equilibrium yield means equilibrium lies to the right hand side, and vice versa. I'm not going to write down the other thing. So be prepared to use that language as well, and you'll see that in a couple of the questions I've got. Right, but as I've said before, we're going to think about pressure, temperature. Maybe if I add a reagent or add a reactant, if I add B, it's going to want to try to remove B, so it's going to go to the right, and things like that. And at the end, if we've got time, we'll have a look at a specific example, look at the Hub process, which is the one that triple students will definitely need to know. Okay? Are we okay? Everything all right? Yeah? You all right? Yeah.
What does it say after?
Position. Lies to the right hand side. Okay, so that's as much as I want to do in terms of a kind of introduction. There's lots and lots of people will, you'll find videos of people talking through this or in your books. That's just kind of a refresher, reminder. I'm going to pause the video and do a bit of practice with you, and then we'll do some exam questions. So a few random questions on the way just to build up. So methanol is broken down during digestion. You just shout out the answer here. Do you know the answer to the question 1? 3, 2, 1. Yeah, so that's easy. Enzyme, right? So we'll move on then. So this is a sort of moles question, really, isn't it? If I've got, this is carbon monoxide. How many moles of carbon monoxide would react with this number of moles of hydrogen? So A, B, C, or D? Everyone? 3, 2, 1. You're not very confident of this. This is what I thought. So when you're looking, no, it doesn't surprise me, so I left it in here. So this is a reminder that when you're doing the quantitative chemistry revision that you'll do for your paper 1, the gas calculations are the ones you find the hardest, but actually they're the easiest. You don't need to work out the number of moles for gas calculations because the ratios of volumes and moles are the same. So if you've got 2:1 ratio in moles, we've got a 2:1 ratio in volume. So if you've got 4.0 times 10 to the minus 3, or times 10 to the 3, sorry, of that stuff, we must have half the number of moles needed of that stuff, right? So it's that one. Happy with that? But I'd really suggest you go over volume calculations as well. Here we go, back into the moles calculation stuff. So I'll put the equation, the equilibria stuff. I'll put the equation up here so you can see it. This is a reminder in your exam that it's worth always looking back at the paper to find out what reaction you're talking about here. It's the reaction between carbon monoxide and hydrogen to give methanol. Everything's a gas. So we'll do this bit, but we'll do it much more you focused this time than me. If you can have a go at answering that question. Go, folks. So this is the point here. So again, as I said earlier on, the explanations in reality are quite complex, but we don't need to get into the real detailed explanations. We're doing GCSEs here, and you're not expected to know the deep theory of it. But for the reasons we talked about earlier on, you would get a lower equilibrium yield, right? Because if the reaction is exothermic in the forward direction, if you increase the temperature, the equilibrium will shift to the left, because the forward reaction is exothermic, and probably what you'd say in the exam, you'd say the reverse reaction is endothermic. That's all you've got to say. And it's that language that people often overlook. They probably don't explain it. But you could also say the reverse reaction is favoured. I spelled that. I think I spelled that wrong. Doesn't matter. Equilibrium shifts to the left. Equilibrium shifts to the left to lower the temperature. All of those things are okay. You can't just say, though, the forward reaction is exothermic, because that's in the question. So if you find yourself repeating something that's in the question, you never get a mark for copying down what's in the question. So watch out for that. That's a common answer. Just writing the opposite down is correct, though. Right. Here's a question, though. 4 marks. This is the point I was making at the start again. This topic is about equilibria, but it's also about rate of reaction. So if it's 4 marks, you've got to use an explanation, so highlighting, looking for the keywords. You've got to explain both factors. It's going to be 2 marks for either factor, I would suggest. So again, have a little chat, and we'll discuss the answer in a minute. So the explanation for the high yield of methanol must be to do with the fact that the equilibrium shifts to the right-hand side. So it's quite easy, isn't it? This is the point about this topic. It's dead simple to pick up. Easy marks here. So the equilibrium shifts to the right. And you might have said to reduce the pressure. But to explain that, which is the second mark, you have to talk about, or look at counting the number of moles on each side. Now, in this particular question, you get away with just saying there's 3 moles of gas. 3 moles on the left and 1 mole on the right, or more on the left and less on the right. But I think you should talk about moles of gas. Often you've got solids or liquids that might be in the reaction, and in those situations you have to mention gas. So you might as well do this on this occasion and all other occasions as well. So more moles, or molecules if you like. Simply that. I mean, I'd even prep myself for 6th form and say 3 moles of gas on the left and 1 on the right, just to be really clear. And then the next bit should be dead straightforward. So the second part is about increasing rate, so more particles. And as I said, I don't know if you came to the session last time, but more particles per centimetre cubed or per unit volume, I should say of gas really. And that's often the thing that people miss out, that mark there, as you did, all right? So watch out for that. And then the bit that people get right and really good at, I found, here is you've got the higher, or the high, you should say high frequency, or higher frequency of collisions. So this topic is about rate and equilibrium, and both factors should be considered. Next one is just about rate. We'll only do this one verbally. The 2 marks are, everybody I think said lower activation energy. Every conversation I heard said lower activation energy. Some of you missed out the idea that's the alternative pathway. Raise your hand if you mentioned the alternative pathway. If they didn't mention the alternative pathway, write that down in your notes now as something that will go on your flashcard. So adding a catalyst, alternative pathway with a lower activation energy. It's 2 marks. It's often the first mark that's missed. How many of you missed out the first mark? The pathway one. Lots of you, I'm sure. Right, why do we bother adding a catalyst without talking about increasing rate of reaction? That's quite hard, I think. I think some of you struggle there. And also, question 9.7 you can think about, which is the effect of using a catalyst on the yield. Again, I think some of you will get this one wrong, and this is why I picked it out. So unsurprisingly, you stumbled a little bit on some of these. 1 or 2 of you had a little chat about other things, but you know, it's Friday after school, so I'm going to be somewhat tolerant of that. But you can't mention increasing rate of reaction, but there are a number of possible answers, right? So if you add a catalyst, yes, it will make it faster, but usually to make it faster, you have to crank up the temperature or increase the pressure, both of which require lots of energy, and that's what we're looking for there. So you can do it with a catalyst, means you can do it at a lower temperature, lower pressure, but in the end that means lower energy or less energy required. But you are allowed to explain why that would be. Instead, you could have said lower temperature. Don't say lower heat needed, lower temperature needed. But I heard a few people talking about cost. Now, in this particular question, they have allowed it about lowering costs, but that often isn't an accepted answer, because sometimes there's cost implications that you're not aware of for changing things. So perhaps have in mind the effect of cost, but try to look for other answers too. So in this particular case, it's an allowable one, but the reason it's a lower cost is because you can do it at a lower temperature and less energy is required. What about 6.7 then? So a very, very common misconception that I want to pick up on here. Where are we? So the effect of using the catalyst. A common misconception is that catalysts would increase the yield of the reaction. It would favour one direction or the other. But if you think about an energy profile diagram, say for an exothermic reaction, the reverse reaction would have the opposite energy profile diagram. If you add a catalyst to that, what happens is you get a lower activation energy, same reactant, same products, but the activation energy is lower. So the activation energy of the forward and reverse reaction are both decreased because the pathway has changed in both directions. And so you increase the rate of the forward and reverse direction equally, so it's no effect on equilibrium position. And you were dead right in your answer that you reduced the time taken to get to equilibrium, which is how I put it, more or less what you said, I think. So that's again an easy one marker which comes up a fair bit. If you look through the papers, you'll see that. Right, so another year then, another question, fairly common kind of standard equilibrium type question. There are 4 marks on that page. Just have a little chat about those and we'll go through them together in a moment. Right, so the first question was around what the solvent is, and really it's just checking what's meant by state symbols, right? So make sure you know that state symbols, solid, liquid, gas and aqueous, and try to get into the habit of writing those down every time there's a balanced equation. And while I think of it, if ever you get asked to write a word equation rather than the balanced equation. That's a common slip as well. So just water there, telling you that water's being used there. That's what the aqueous refers to. Right, if you chuck some of this colourless thiocyanate into this particular reaction, that is going to alter the position of equilibrium. As you might have heard us talking about just then, if you chuck in something, either reactants or products, the equilibrium is going to shift to try to remove those. So, pointing to the side of the room that the equilibrium is going to shift, is it going to go to the right or to the left, please? Point right or left. Yeah, good. So that's one of your marks. And if you wrote that down, tick it off. So equilibrium shifts to the right hand side. That's a mark. And therefore, what happens to the colour? Does it become more red or more yellow? Shout out, more red or more yellow. 3, 2, 1. Red. See, it becomes more red. So that's your second mark, more red. And the explanation for it is where it gets, I suppose, a tiny bit more difficult, which is to say to reduce. This is the language that I want you to practice. The reason you're here tonight, the thing you take away from this, is it's shifting, it's doing all that stuff to reduce the concentration of SCN- or thiocyanate. Okay, that was the third mark. How many out of 3 did you give? Show me with fingers how many you got. We'll stop at 10, probably 10 past today, or maybe a whisker after. But let's have a go at those first 2 questions, please. So, because it's becoming more yellow, the equilibrium must have shifted to the left, and then we've got to explain that, and that must be to, given we know that the water bath is above room temperature, it's shifting to the left, presumably then to cool down, suggesting that the reverse reaction is endothermic, or the forward reaction is exothermic. So you'd say to reduce temperature, because reverse reaction is endo, or you could say the forward reaction is, oh, it does talk about the forward reaction in the question here. So because forward reaction is exothermic. So your scores, please. Little random question at the end. Votes for A, B, C or D, and then we've got one more question and we're done. So are the metal ions, what other, well, go and read it and tell me your answer. So this question caught everybody out in the mock. So other metal ions form a coloured equilibrium with the thiocyanate ion. Remember, the thiocyanate ion we were told earlier on was colourless, but other metals form coloured mixtures. So only one of these metals is a metal that's coloured when it's a compound. You need to know from the periodic table, or trends in the periodic table topic, something about metal compounds that are coloured, and it's only those that are transition metals. And you're expected to know that. That is an important point that's easily overlooked. I haven't done a session on periodic table and whatnot, but I probably will next time in preparation for, or the time after in preparation for your paper 1. 4 or 5 minutes on this, then we stop. All right, okay, 4 or 5 minutes on this, we'll go through it, then we stop. We'll work this through as per the mark scheme here, and you can sort of tick off the things that between you were saying. So I would really encourage you to try to sort of organise your thinking in terms of rate and yield in particular, and that will apply to all of you. I think the idea of some compromise factors, so compromising factors, is really something which is directed more at the triple students. I know there's a mixture in here, so we'll consider that, but I think and it kind of relates then to the harbour process, which we're not going to talk about. I'm sure you'll cover that in class over the next week or 2 as well. So to make it as economic as possible, you're going to want as fast a rate as possible, right? Yeah, so what factors are you going to do to increase the rate? Well, you're going to increase the temperature. And you explain that by talking about increased frequency of collisions, like we did last time. And you're also going to talk maybe about increase the energy of those collisions as well, and all the kind of stuff that we went through last time. Also, to increase the rate of reaction, you're going to increase the pressure. Again, because you're going to increase the frequency of collisions if you've got a higher pressure. All the reasons we talked about last time you could add in here, you know, the idea of number of particles per unit volume. And there's another thing you could do to increase the rate of reaction as well, which is to add a catalyst. I'm not going to go through the explanation now, we've already done that even today about the lower activation energy and so on. Right, more of today's, but you see again, the questions are about both rate and equilibrium, right? They're about rate and equilibrium. So we covered the rate briefly, only briefly, but it's there. And you would go into a bit more detail in your exam. But we've got to think about the effect of those factors on the yield as well. So you want to give, to increase the yield, it's slightly different in the mark scheme how it's set out, but to increase the yield you want a low temperature. And you'd explain that because reaction is exothermic, just for all the reasons we talked about earlier on, right? And I heard you talking about that. You'd also, to increase the yield, because there are 2 moles of gas on the left and 1 on the right. And again, mentioning the number of moles of gas, not just moles of stuff. But to increase the yield, you increase the pressure as more moles of gas on the left-hand side, and the equilibrium will shift to reduce the pressure. And so you're already picking up heaps of marks here. You might also consider, and that's kind of the bulk of what we need to do, but you might also consider the effect of those things on cost. So increasing pressure and increasing temperature increase cost, more energy requirements, or you might need to have thicker lined walls of your reaction vessel if you've got high pressure. So think about the things that can affect the cost. But particularly for the triple students, we've got to think about the compromise. I don't know what I did there. Compromise. And you can see that we want a low temperature and we want a high temperature. So really we want something in between the two. And you could also say, well, high temperature favours the rate, but low temperature favours the yield and lowers the cost. So it's a compromise between all of those things. And of course, and I'm not going to go through this question, but you can see that other questions consider, it's worth looking at this question. I'll leave it on here. You can consider and look back at, so the 2019 paper is a really good paper on the effect of temperature on yield and rate, and you've got to be able to interpret graphs like this to consider the effect of temperature on rate and yield and all that kind of stuff. All right, so I'll leave it there and we'll head off, but I hope that was somewhat useful.